It's not. Let's pick up where we left off. Yesterday we introduced exponentials, and we talked about these important points. This summarizes the parent graph of an exponential. So remember, we call this exponential base A. The base is a positive number. It's not equal to 1. And the variable is in the exponent. So we call that exponential base A, and it always goes through -1, 1 over the base, or in other words, -1, the reciprocal of the base, 0, 1, and then 1 comma whatever the base is. The reason we graph these 3 points is that's where the bend occurs. That's where the most shape change happens. Okay. Again, the base has to be a positive number other than 1. If it's a number bigger than 1, we call that exponential growth. If it's a number between 0 and 1, like a fraction 3/4 or 1/2 or 1/4 or something like that, then it's going to be exponential decay. It's going to decrease like this guy right here does. The domain, you can plug in anything you want. Any number you want to plug into an exponential is totally okay. As far as the range goes, the only numbers we get out are positive numbers. So the domain is from -infinity to infinity. The range is from 0 to infinity, not including 0. And that's because we've got these horizontal asymptotes out here on this end. Y equals 0 is a horizontal asymptote out here, and y equals 0 is a horizontal asymptote out on the right end of a decreasing exponential function. Okay, so we talked about the transformations that we're already familiar with when we're dealing with parabolas, quadratics, things like that. Slide it left, right, up, down, stretch it, shrink it, flip it upside down, stuff like that. And then we graphed a few of these, graphed several of these. And you'll notice that on each one of these, I graphed the original function, like exponential base 2 here, exponential base 2 here. Here's what exponential base 2 would look like. And then on this particular one, we slid the graph up 3 units and to the left 3. And then we figured out where do those 3 key points end up. So this idea of making the correct shape and then sliding it where we need to is a really important one. That's going to pay off big time, especially when you take 1060. We did this one right here. This was 1/8 to the x, exponential base 1/8. That decreases, it decays very, very quickly. Okay, and again, notice those 3 points. If you were to plug in 1, 2, and 3, you'd have what almost looks like a straight line. It hardly has any bend to it. Okay, those 3 key points are really important. Okay, let's take a look at this one right here, because this one gets to be kind of interesting. We left off on example E. This one had a vertical flip, and it had a horizontal shift and a vertical shift. We ended up with these points, and you'll remember we took that point right there, we plugged it in, and we actually showed that it works. Okay, so we're not just making up points. They do actually work in the equation, and it's a lot easier to produce an accurate graph by thinking about what shape it makes and then slide it around than it is by plugging in points. Much, much more efficient. Okay, so let's take a look at this one right here. Does anybody have any ideas on what would happen? Because the only thing we did with this is we multiplied the x by a negative, or we replaced the x with a negative x. Any ideas there? John?
Wouldn't it kind of make it exponential base 1/4 because that's already negative?
It would. Very good. What does the negative in the exponent mean? Okay, it means reciprocal. Okay, so this would mean 1/4 raised to the x. Okay, now technically this is exponential base 4, right? Exponential base 4 normally looks like this. It goes through 1/4, 1, and 4. So it normally would look like this. This is the original graph. But when I multiply the x by a negative, or when I replace the x with a negative x, I get a shape that's like this. This isn't exponential growth, this is exponential decay, right? So let's graph a couple points on this. This would go through -1, 4, right here. Plug in a 0, you get a 1. And plug in a 1, you get a 1/4. So how does this graph compare to the original one? It is reflected. Okay, we're going to call it a horizontal flip. Okay? Flips it across. This seems a little bit weird, but flips it across the y-axis. By replacing x with a negative x, you flip it across the y-axis. If you multiply the x with a negative x, okay, what would this do? I'm going to change colors here. So instead of multiplying the x by a negative, what if we multiply the function by a negative? What would that do? That would be a vertical flip. So it would look like this. It would go through here, here, and here. Okay? So the red dotted graph, that's the original exponential base 4. This is multiplying the x by a negative. Okay? It's a horizontal flip. And this is multiplying the function by a negative. That's a vertical flip, just like we're normally used to. And again, we could go through and we could label the points here, even though that doesn't look like it. Mine kind of looks like garbage. This is the point negative 1 comma 4. This is the point 0 comma 1. And this is the point 1 comma 1/4. And again, it's got a horizontal asymptote of y equals 0 out on the right end out here. Are there any questions there? Yeah.
So would you name it exponential base 1/4, or would you still call it?
I would call this exponential base 4. Okay? If you wanted to rewrite it this way, then we could call it exponential base 1/4. What I'm more interested in the time being is we know what function we're dealing with. We're dealing with exponential base 4. Okay? So we know it's this dotted red shape right here. We know the key points that that goes through. And what happens when we multiply the x by a negative? It's a horizontal flip. So this point here flips over here. That point stays the same because it's right on the y-axis. And this point right here flips over there. If we were to multiply the x or the function by a negative, that is a vertical flip. Okay? So we want to understand the difference between multiplying the x by a negative and multiplying the function by a negative. Multiplying the x by a negative changes it in the x direction. It's a horizontal flip. Multiplying the function by a negative changes the y coordinate. It's a vertical flip. Okay? Got that? Okay. Let's take a look at a couple more. Let's slide over here and let's take a look at this one. Okay, now please don't say anything out loud. Don't want to embarrass anyone, potentially. So the question here is, we need to know what shape this is, and we know what shape it is based on what function it is. It's exponential base something. I'd like you to think, again, don't say anything out loud. This is exponential base what? Don't say anything out loud. And then I want you to consider this. We're really familiar with that shape right there. And we're also familiar with what would happen to that shape if we multiplied it by 3. Okay, exponential base what? You can say it out loud now. Exponential base?
2.
It's exponential base 2. It's not exponential base 6. Okay, remember the exponent only applies to what it's over. It only applies to what it's over. If we wanted it to be exponential base 6, we'd have to put that in parentheses. So this is exponential base 2. So if we figured out what the original function looks like, remember it's going to go through 0, 1, 1, 2, and negative 1, 1/2. It's going to look something like this. It's going to have that horizontal asymptote out here. Everybody good with that? What does the 3 do to this type of graph? It's a vertical stretch. It makes the points 3 times taller, or it makes the graph steeper, right? So instead of graphing this one right here at over 1 and up 2, we're going to go over 1 and up 6. Instead of being at 0, 1, we're going to be at 0, 3. Instead of being at negative 1, 1/2, we're going to be at negative 1, 3/2. Very good. I had a lot of people say that right now. Now, if the old horizontal asymptote was y equals 0, what if I stretch 0 by a factor of 3? Stays the same. It's still 0. So I still have a horizontal asymptote of y equals 0. And remember I said if you're going to draw an accurate graph, it's really helpful to draw that horizontal asymptote before you start connecting points. So I'm going to run along here. I'm going to hit that point right there, hit that point right there, and then go like this. Now, does it look like this particular graph is 3 times steeper or 3 times taller than it used to be? We didn't slide it anywhere. We didn't go up, down, right, left, or anything like that. All we did is we take every one of those points and we made them 3 times taller. Okay? So this point right here, instead of being 1, 2, is 1, 6. Instead of being 0, 1, is 0, 3. And instead of being negative 1, 1/2, it's negative 1, 3/2. Now, let me stop right there. Are there any questions? Because if you get this, we're in pretty good shape. And if you really get this, then we're in good shape for the next section that we're going to cover, which is logarithms, which we're actually going to start today. Any questions? Okay, so let's take a look at this one. Don't say anything out loud. I'll ask you in just a second. I'll tell you when it's okay to say something. Exponential base. Exponential base what? Exponential base 1/2. That means we know what the parent graph looks like. That means we know that it goes through -1, 2, 0, 1, and 1/2. What does this -4 do to the graph? Okay, say that again, Sid. Okay, it's a vertical stretch and it's a flip. So instead of going like this, we're going to flip it upside down and we're going to stretch it. So instead of being at back 1 and up 2, we're going to go back 1 and down. What is it, Zach?
8.
Down 8. We don't just go down 2, we're going to go down 4 times as far, so we're going to go down 8. So we're going to be about right here. Whoops, let me change colors here. So this is going to be -1, -8. Instead of being at 0 and up 1, we're going to go to 0 and
4.
down 4. We're going to be down right here. So this is going to be 0, -4. If I normally went over to 1 and up to 1/2, I'm going to go over to 1 and now I'm going to go down 4 times as far as 1/2. 4 times 1/2. 4 times 1/2 is 2. So we're going to go down here to 2. Okay? Now, do we change the asymptote?
Nope.
We don't. It's still going to be y equals 0. So again, if you draw in that horizontal asymptote, then draw the sketch of the graph, you're more likely to draw an accurate picture here. Again, this point was 1, -2. Just for the heck of it, let's plug in a -1. We better get out a -8. So let's see what happens. If I have -4 and 1/2 to the -1. Reciprocal right here, right? So that's going to be -4 times the reciprocal is 2, so we end up with -8. So does it work? We got the correct graph only knowing about the shape. We knew about the shape of exponential base 1/2. We knew that this was a vertical stretch and a flip, and we came up with the correct graph very quickly with 3 key points and an asymptote that helps us draw the graph correctly. Are there any questions? Okay, let's take a look at the next one. Has anybody seen this before? Okay. Okay, E is called the natural number. Okay, E is approximately 2.71. It's a big, long, irrational number. It's kind of like the number pi. We call it the natural number because it comes up a lot in nature. It's just amazing where this number crops up in formulas, population growth, different things like that. It's a really important number. So lock away in your head, if you already know that pi is 3.14159, blah, 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 it goes on forever, never repeats, lock into your head that E is approximately 2.71812, I think is what it is.
How many places do you need?
2.7 is fine. 2.7, 2.71 is okay. Somebody have a calculator that can throw that in real quick? Let's do that. You've got one on your calculator. Let me just make sure. So here is the letter E right there. Yep, 2.718. Oops, just 82. Okay. All right. So is this a number bigger than 1 or less than 1? Bigger than 1. So if this is, what would the name of this be? Exponential base? Exponential base E. Am I going to have exponential growth or exponential decay? Growth. So that means it's going to go through 0, 1, 1 comma E, which was going to be about 2.7, and 1 over 2.7 here. So that's going to be about 1/3, so it's going to look something like that. We're going to have a horizontal asymptote of y equals 0. This is what exponential base E looks like. Doesn't look very special, doesn't look like it's any different than the other ones that we've had. We do want to label these points right here, 1 comma E, 0 comma 1, and what's this one? -1 comma 1 over E. Okay, that's how you'd write it. Okay, are there any questions there? Sure? Okay, that is exponential base E. I would make sure that you know that. Okay, now we're going to do a couple of these. It says state the range, domain, range, and horizontal asymptote. I think we've written the horizontal asymptote on every one of these. Let's do A and B. What's the domain here? Okay, you can plug in anything you want, right? So the domain would be from negative infinity to infinity. What about the range? So if you squish it onto the x-axis for the domain, you squish it onto the y-axis for the range. Okay, not quite 0 because remember, we moved this up. See where the horizontal asymptote is? So we'd only get answers starting at 1 going to infinity. So this would be 1 to infinity. Well, wait a minute. This is an exponential, right? Can't you plug in anything you want? Domain is from negative infinity to infinity. What about the range on this particular one? Find the asymptote. Did it change at all? It didn't, so it's going to be from 0 to infinity. It's going to be from here up. That asymptote is key to figuring out what the range is. Okay, let's take a look at this next one. Domain. My gosh, it's an exponential. Negative infinity to infinity. You can plug in anything you want into an exponential. What about the range? It's going to be 3 to infinity. Okay? Let's take a look at E. Take a look at this one right here. So on E, what about the domain here? Negative infinity to infinity. And the range? This one's a little bit interesting because what happened to this graph? Got vertically flipped. So we don't start at the horizontal asymptote and go up. We kind of start there and go down. So what would be the best way to describe this? Put it in the right order. Negative infinity is smaller than negative 2. So we'll start down here at negative infinity, and then we stop when we get to negative 2. Okay, are there any questions there? What's the domain and the range for this last one, exponential base E? All reals, negative infinity to infinity. And the range? We didn't move it anywhere, so it has the same thing as any other parent graph function for an exponential. It's 0 to infinity. Okay, any questions? Okay, just a reminder, you do have, your homework is out of the textbook. Okay, so you want to make sure that you bring your textbook and get started on that homework assignment. We're going to look at two problems that are similar to the ones on your assignment. This is problem number 43. It is a story problem, but please don't let that scare you. Read it, look at it. A lot of times they'll give you a formula or plenty of information to figure out what the answer is. Take a look at this one. It's talking about whaling in the mid-70s, humpback whales, endangered species, all that sort of stuff. Talks about the worldwide population. And then it gives this equation right here. P of T. What do you think P stands for? Population. What do you think T stands for? Time. So that means if you plug in a time, it will give you the population of whales. So it says, how many humpback whales were alive in 1930 and in 1960? So notice that it says T is the number of years after 1900. So if it were 1930, what T would we plug in? Plug in a 30. If it were 1960, what T would we plug in? 60. It's literally that simple. So we're going to figure out what 150.96 raised to the 30 is. That's going to be the population in 1930. And the population in 1960 is 150.96 times 60. Now, before you type anything into your calculator, you should know roughly what to expect. Isn't that right? Okay. Is this exponential growth or is this exponential decay? And how can you tell? Christopher, which is it? How can you tell? The base is less than 1. So let's grab the calculator and let's just type this in. I'm going to clear this off. 150 times 0.96, and then we'll raise that to the 30th. Now, if you've got more than one term in the exponent, make sure you put that in parentheses. That's our answer right there, 44.07. Really, 44 whales? Says 44.07, and it says in thousands. So I'm going to move this over 1, 2, 3 places. So this is 44,070 whales. And then do the same thing with this next one. With this next answer, if I just recall this and I change this to a 60, am I expecting a bigger number than 44,000 or a smaller number? Should be smaller, okay? So we'd have 12,952 whales. Sound okay? Good with that? Graph the function. We're looking for exponential decay, right? We're expecting it to go down. Now, I've got a couple points on here. I've got 30 and 44.07, and I've got 60 and, what was that, 12.9 or something like that? Okay, so these are the points that I've got. What if I plugged in a 0? Don't say anything out loud. What if I plugged in a 0? Well, if this is exponential base 0.96 and I plug in a 0, what do I get out of this part of it? I get a 1. 1 times 150. So just like on the other ones, we stretch this. This is going to cross at 150. At 30 years, it's going to be down to 44. So maybe we should do that. And at 60 years, it's going to be down to 12. So it's going to look something like this. Theoretically, what's going to happen to the population of whales? They're eventually going to be gone. Okay. Any questions? Okay. Take a look at this problem right here. Does anybody have their textbook? Okay. John does. Impressive. Okay. This says that they want you to graph this. Okay, what's different about this problem? Okay, it's x as a function of y, not y as a function of x. We normally see the y's on this side and whatever the expression is with an x in it over here, right? So this is different. Okay, but this is still an exponential, right? So in this case, it would actually be easier to plug in the y's. Well, guess what y's we're going to plug in? -1, 0, and 1. What's this one going to be? A 1. What's this going to be? A 1/6. And what's this going to be? Okay. So you'll notice that all we did is where we normally had x's and y's, we just kind of switched those. So it's kind of like we had those backwards. So if I were to sketch this, 1/6 and -1. So that would be about right here. 1, 0 would be about right here. And 6, 1, 1, 2, 3, one more, there we go. Okay, I'm not a huge fan of this, but it does illustrate the point, and that's how you do that particular problem. Okay, are there any questions? Okay, we're going to take about a 2-minute break. I'm going to pass out the stuff for 9-3, and we'll go from there.